In this problem, we are given the beam shown, and it is supported by a roller at B and hinge at B. The beam carries the following load: concentrated live load of 100 kilonewtons, a uniform live load that is 50 kilonewton per meter. We are tasked to compute the maximum positive shear, negative moment, and positive moment at C. To solve this problem a lot easier, we can make use of the concept of Muller-Breslau principle. So by cutting on this segment here, we expose the shearing forces at point C. Based on positive sign convention, the shearing force on the left side of the beam, this is moving downwards, and for the right side of the beam, this is moving upwards. Using Muller-Breslau principle, if we try to imagine what will happen to the beam if these two forces will tend to act on this point, it will tend to rotate the beam in this manner. And on the right side, it will somehow move like this. And this is the graph of our influence line diagram based on the rotation of the beam. And the value for the negative shear at this point, this is the ratio of the distance going from the support towards the point where we cut the beam. This is A, and this length, remaining length here between the support on the right side towards the point where we cut the beam, this is B. So this value of negative shear, this is A over A plus B, and for the positive shear, this is B over A plus B. And we have A here, there is a value of 3 meters, so this is 3 over 3 plus B, that is 6. So this value right here is negative 1/3. And it is negative because it is below the horizontal axis. There is a value of 0. And at this point here, this has a value of positive 2/3. And this value right here, by ratio and proportion of these two triangles, since this two triangle here has a length, base length of 3 meters, therefore we expect this value here to be just equal to 1/3. Now to solve for the first problem, to get the maximum positive shear at C, we apply the concentrated live load of 100 kilonewton to the point where the shear is positive and maximum. That is at this point here. There is a value of 2/3. And for the uniform live load, we place the uniform load between the segment where shear is positive, which is between A and B, and C and D. Now solving for the positive shear, we multiply the point load by a factor of 2/3 and the uniform load by the area of these triangles. So the maximum positive shear, that is equal to 100 kilonewton times 2/3 plus 50 kilonewton per meter multiplied by the area of this triangle, that is 1/3 times the base of, this is 1/2 times the base of 3 meters times the height of 1/3 plus the uniform load 50 kiloNewton-meter per meter multiplied by this area of this triangle, that is a base of 6 meters. So this is 1/2 times the base of 6 meters times the height of 2/3. Now solving, we have 100 times 2/3 plus 50 multiplied by the area of this right triangle between A and B, plus another 50 times the area of the right triangle between C and D. We get our final answer, that is equal to 191.67, or approximately 192. For the second problem, to compute for the maximum negative shear at C, we will move our concentrated live load just to the left of C So it is the same point right here. And for a uniformly distributed load, we place this between B and C, where the influence line diagram is negative. Now solving for the maximum negative shear, this is equal to 100 kilonewton times a factor of negative 1/3 plus 50 kilonewton per meter multiplied by this area of this right triangle, that is 1/2 times the base of 3 meters times the height of negative 1/3. Now solving, we get our maximum negative shear. That has a value of negative 58.33. And for the last problem, to compute for the maximum negative moment at C in kiloNewton-meter, we will make use of the principle or the concept of Muller Breslau. So we're cutting at the same point at C. Now instead of focusing for the shearing force, we'll begin focusing on the bending moments applied. So based on positive sign convention, the bending moment on the left side of the beam, this is acting counterclockwise, and on the right side this is clockwise. Now if we try to imagine what will happen to the beam if we apply those bending moments, and cutting at this point, it will tend to rotate the beam in this manner, and on the right side it looks like this, and this is the shape of the influence line diagram of this beam. And resolve for the value at this point, this is equal to A times B over A plus B. So we have A here that is equal to 3, and B that is equal to 6 divided by A plus B. This value here is equal to 2. And this value here, using relation proportion, since these two triangles have equal bases of 3 meters, therefore we expect this value here to be equal to negative 2. And this one here is 0. Now to compute for the maximum negative moment, we will place our concentrated load to the point where moment is negative and maximum, which is at this point here. And for the uniform light load, we'll place this between A and B, where the area of the influence line is negative. So to compute for the maximum negative moment, this is equal to 100 times a factor of negative 2 plus the 50 kilonewton per meter uniform load multiplied by this area of this triangle, that is 1/2 times the base of 3 meters times the height of 2 meters. This has a value equal to this sign here should be negative, because the value here is negative 2. That is equal to negative 350 kiloNewton-meter, which is letter D. And to compute for the maximum positive moment, we will move our loading to the point or between the segment where the influence line diagram is positive and maximum. So our concentrated live load will be placed at point C, where it will have a factor that is positive 2. That is the point where moment is maximum. And for the uniform load, we will place this between B and D. So to compute for the maximum positive moment, this is equal to 100 times 2 plus the 50 kilonewton per meter multiplied by the area of this this large triangle, which has an area equal to 1/2 times the base of 9 meters and a height of 2. We will get our maximum positive moment that has a value equal to 650 kilonewton meter, which is letter D. And these are our final answers.